All right, welcome back to chapter number 3. We're going to talk about molecules, compounds, and chemical equations. Mostly we're going to talk about how to name things. Just as a warning, I give this to all my students on each of your exams. Exam number 1, because we're covering it here. Exam number 2 and exam number 3, there will be a section of naming. We need to practice our naming so much to where it becomes secondhand, because on your final, some of the questions will just say react sodium hydroxide with hydroiodic acid, right? And so obviously right now, just hearing those, you're thinking, oh, I don't know what those are. That's okay, because we're going to learn how to name those, and we're going to practice. Same thing in your lab. Your lab is just going to put up some names like potassium permanganate. And so we need to know what those are so we make sure that we're using the right chemicals in the lab and we can get the right results. So I just want to preface that up front. The other thing I want to say up front, we're going to get to it later in the discussion or in the PowerPoint, but I just want to bring this table 3.4 up to the front here. These are some common polyatomic ions. You need to memorize this table. You need to know that OH is a hydroxide. We're going to talk about why these are special later. But, carbonate, hydroxide, nitrite, nitrate, chromate, chlorite, chlorate, perchlorate, permanganate. We need to know these things, phosphate, because we're gonna need to know those when we talk about ionic compounds as well as acids. And so we do need to memorize table 3.4, especially before the first exam, and even we need to memorize it, and then we need to keep it and keep the naming throughout all the other exams. So let's talk about elements. Let's talk about molecules, right? And that elements can combine chemically with each other. And what happens is the resulting is usually a completely new substance. So let's look at hydrogen and oxygen. Hydrogen and oxygen are two gases with a very, very low boiling point. Since they are gas, their flammability is different, whereas hydrogen is very flammable and explosive. If you've ever seen a video of the Hindenburg, that is what they used to fill balloons that would go into the atmosphere with, was hydrogen. Very, very flammable gas. Oxygen, however, is a relatively inert gas, right? Like you're not going to light a match and it's just going to catch on fire. However, oxygen is required for combustion. If you don't have oxygen, you won't have fire. But you put them together, and you can just see the properties, how they've changed. The boiling point has raised rapidly. It now becomes a liquid instead of a gas. And instead of causing fire and being needed for fire, it is used to extinguish fire and actually to keep us healthy when we drink it. And so elements combining are very, very important in what we're going to be studying. Now, there are two types of chemical bonds that hold some things together. There is the ionic bond. Ionic bond is formed between two ions. And one of the things that we're going to see, again, we talked about neutral charge when we talked about ions, right? That all elements are neutrally charged. Well, if we form an ion, let's say we form a cation with sodium. And so sodium forms a cation at +1 is the charge. And let's say we have chlorine. Well, chlorine steals that electron, and so it becomes -1. And so we now have a +1 and a -1. Well, those things don't like to be charged. So they look at each other and say, hey, let's get together. Okay. And so then they come together. Now we know that as table salt, sodium chloride, NaCl. But that's why we form an ionic bond, is to neutralize charge. A covalent bond is not necessarily formed between two ions, but it's formed between two elements where they share their electron, right? So let's say hydrogen and oxygen, they're looking at each other and they're saying, hey, you want to share? Sure, let's share. And so then that's how they form together. Obviously, this is a very broad, basic overview of what's actually happening with this covalent bonding, but they're sharing the electrons. So how do we depict these bonds, right? We or these compounds that are now made. There's different types of what's known as chemical formulas, and these are important to know. At least the first few we'll talk about are very important to know. We'll talk about some more in the next slide that we'll be doing in lab. The first one is the empirical formula. The empirical formula just gives us the relative number of atoms. So in this example, we're looking at hydrogen peroxide, H2O2. The one in the middle, where it just says H and O, that is the one that's the empirical formula. We will learn how to calculate empirical formulas in this chapter, and using what's known as a combustion analysis to calculate that, right? To just find out the basic numbers of these elements in this compound. Then you have the molecular formula. Molecular formula gives you the actual number of atoms. So H2O2, there's 2 hydrogens, there's 2 oxygens. That's the molecular formula. And then we could even show how they're connected to each other through what's known as a structural formula. We'll talk about the different types of bonds at the end of the class, about single bond, double bonds, triple bonds. But just know that a structural formula tells us how things are bound together. Now, if we were to look in real life, it wouldn't look just like an H, an O, an O, and an H. And this is where we get things like the ball and stick model, right? And what you can do is you can take the ball and stick model, right? We have 2 examples, the one on the bottom and then the one on the right in the middle, where you're showing the atoms as pretty big size, and you show all the bonds as sticks. Now this will show the molecular shape. When we talk about molecular shapes, this is why this is going to come in at the end, is we're going to start using a lot of these. Now the space filling model is if we were to be able to have a high powered microscope enough to go zoom in on these compounds, this is how it might look. It is the space filling model, the bottom on the right, and then the one on the far right in the group of methane, CH4. And so the one on the right, just to let you guys know, is caffeine. That's what caffeine looks like. And then the one on the bottom is methane, CH4, carbon tetrahydride, and the space filling model. You can just see that they're different sizes, right? But there's not a lot of space in between. And so if we were to scale these up, this is what they might look like. And so why, we'll talk about why we care about those later on, why we care about the shapes. It has a lot to do with pharmaceuticals and things like that. But some elements are unique in that they're not found as a single element, as they're not found alone. And these are usually found with gases. We're going to talk about gases specifically. There are others that are non-gas that also have this type of polyatomic element. So the atomic elements exist in nature with single atoms as their basic units, right? So things like sodium, potassium, calcium. This is the majority of the periodic table. However, there are some elements that are form molecular elements. These do not exist in nature as a single element or as a single atom, if you will. And so, again, pure substance elements, right? So we're going to see this again. So that you have a pure substance. We can break it off and divide it into either elements, right? Pure elements, things that you see on the periodic table, or compounds, right? Compounds are usually more than one element. And you either have molecular, which is by a covalent bond, or ionic, which is, we talked about, like sodium chloride. And then you have, or with the elements, you have atomic elements, the majority of the periodic table, like neon, sodium, magnesium, or molecular elements, things like oxygen, nitrogen, fluorine. Non-metal elements are usually found as molecular elements, right? And so we should be familiar with, hint, hint, nudge, nudge, the elements that exist as diatomic molecules. Now, this is very important because let's say I give you a question, how many moles are in 3 grams of nitrogen gas, right? So how many moles are in 3 grams of nitrogen gas? Well, if you didn't realize that nitrogen was a diatomic molecule, your molecular weight that you would use would be half of what it needed to be. So then your answer would be half. And so these are just some of the things, and that question would not be used to trick you. That question would be to see if you remember, right, the diatomic elements. That's not a gotcha question. Some questions unfortunately are, but that wouldn't be. I would use that to just show or to see, maybe just let's see if we've learned which ones are diatomic elements. And so the ones in the yellow are more important. So phosphorus, I believe, is P4 or P5. Sulfur is the same. But we don't have to worry really about those. I'm more worried about the gases, the things in yellow than the things in that orange color. So let's talk about naming things. We need to name compounds. So let's start with ionic compounds. Ionic compounds are the simplest. In my mind, they're the simplest because they're all named exactly the same way. And so they always contain a positive and a negative. The sum of the charges must be the same. Now, here's where we need to start thinking about, and I'm going to give you guys a trick. Looking at the periodic table, we'll go back to the periodic table, and I'm going to give you guys a trick on how we know what charges are. So then we can start thinking about memorizing just the charges, and then we can start understanding why these have the charges they do later on in the semester. I really don't like the layout of this, but it's what we have to work with. And so the formula of the ionic compound reflects the smallest whole number ratio of ions. So if we look at a salt cube, there's hundreds of thousands of sodiums and hundreds and thousands of chlorines. But what we're looking at is just the fundamental unit of that salt, if you will. And so let's talk about naming things in a minute. All right, so there are many ways to name ionic compounds. There's the common name, right? So sodium chloride is table salt, sodium bicarbonate is baking soda. We are not going to deal with the familiar compounds or the common name. So if I were to put NaCl on an exam, I would expect you guys to do the systematic names, to name it using the systematic name as opposed to the common name. Systematic names are chemists give the name that chemists give to these compounds, and it's a step-by-step process. Again, it's going to take practice. Usually, and for the purposes of this class, an ionic compound will be formed between a metal and a non-metal, right? A metal and a non-metal. Because remember, metals give up their electrons, forming cations. Non-metals steal those electrons, becoming an anion, positive and negative, coming together to form that compound. And so let's see how we can start to name these compounds. So naming an ionic compound where the metal forms only one type of cation. You're thinking, what do you mean just one type? We're going to talk about that in the next slide, what happens, and just some different examples. So the metal in an ionic compound always retains its name, right? So let's say you see K is potassium, Na is sodium, Ca is calcium, Mg is magnesium. Where the metal retains its name, so potassium, sodium, and then what we do to the non-metal is we drop off the ending, so the base name of it, and we add "ide" to it. So chlorine, chlor is the base, and then you just add "ide," so chloride. Now, as we're looking at this periodic table, something to note, the things in the light yellow on the far left, along with silver, those are +1. Right? Those will always be +1. The ones in the darker yellow, just one group over, are always +2 along with zinc. And then you get the ones in the brown. More specifically, look at aluminum, Al. That's always going to be +3. We need to know those, right? We need to be familiar with those charges. Now, the non-metals, let's look at group 7. So starting with F, fluorine, chlorine, and all those are always -1. The group over, oxygen, is always, and sulfur are always -2. And the group over, nitrogen and phosphorus, are always -3. So we just need to know those. We need to memorize those, whatever it will take for you, right? Because we want to make sure. So let's say we put a magnesium with a chlorine. Well, magnesium is +2, chlorine is -1. How many chlorines would we need to neutralize that +2 with chlorine being -1? Exactly. We would need 2 chlorines to neutralize the +2 charge. And so, but the name stays the same. It doesn't matter how many chlorines or magnesiums or sodiums that we have. it is still going to be magnesium chloride. So now let's say we're going to talk about a transition metal, right? Transition metals are those, again, in between the main group elements. And these are kind of strange. They're weird because they can have more than one charged cation. Now, they always form cations, but it can be a different cation. And so the way we're going to name those is we're going to name them the same way we did before. So for iron, we're still going to put iron in there. For copper, we're still going to put copper. For tin, we're still going to put tin. But in this case, we're going to have to be aware that iron has multiple different charges. And so let's say we have an iron plus 2. So then you would say iron, and then in parentheses, you'd put the Roman numeral 2, so 2 I's, and then you would put, let's say, chloride. So iron 2 chloride. I'm going to put a practice sheet up with these names. There are also practice problems on your online homework that'll help you work through these. I pray and I hope that you guys will let me know if you need more work and we need to kind of talk about these in a little bit more detail one-on-one or even in a group setting. We talked about those polyatomic ions, the table 3.4. This is an ion composed of 2 or more atoms. We need to know this. We need to know this book, or we need to know this. Now, how do we name with these, right? How do we name with these? Let's say we're looking at sodium hydroxide. Well, I just named it, right? So OH is hydroxide. That keeps its name. The metal keeps its name. So then what you have is sodium hydroxide or sodium phosphate, sodium chloride, sodium nitrate, right? So it's the same way to name. It's the same way to name. You keep the iron or the metal the same, and then you just have to change the name on the end. Now, again, if we had iron hydroxide, it would be either iron 2 hydroxide, iron 3 hydroxide. Now, you might be asking me, well, Dr. Bishop, how am I going to know if it's iron 2 or iron 3? I'm going to answer that question right now. So how are we going to know if it's iron 2 or iron 3? So let's say we have 2 compounds. So we have iron chloride. Both of these are iron chloride. So how in the world are we going to know if one is iron 2 chloride and the other is iron 3 chloride? Well, the number that we need to look at is this one right here. Because if you remember, what did we say the charge of chlorine is? That's right, it's a -1 charge. Well, how many chlorines do we have up here? Well, we have 2. What's the total negative charge of these chlorines? It's -2. What about down here? What's the total charge of these chlorines? -3. So to neutralize this -2 charge, what does the iron have to be? Exactly. It has to be a +2, right? Because we want these to equal 0. And this one down here is going to be +3. That's why we have to know the charge of the anion, right? So now we have iron 2 chloride and iron 3 chloride. And again, one of the things that we're going to have to do for these exams is we're going to have to both name, right? I'm going to give you a formula. You're going to have to name it. And I'm going to give you a name, and you're going to have to write the formula. Again, at the beginning, test number 1, they won't be too difficult. I don't want to say they'll be easy because, then a student will say, Dr. Bishop, I thought you said this was going to be easy. But they'll be on the easier side. And then as we progress through the semester, they might get a little bit more difficult. The last set of ionic compounds we're going to talk about, and then we're going to be done with naming ionic compounds. It's a long list of ionic compounds, but they're named almost exactly the same way, just with a little additions, right? With a little decorations. In the end of part 2 of this, we'll go back to a review section and just a way that we can follow a few different things to make sure we're naming things the right way. Some ionic compounds contain a specific number of water molecules. And what these water molecules do is they just kind of surround the ionic bond, it's known as waters of hydration. They're known as hydrates. They're named as other ionic compounds. However, they're given the prefix, whatever number there is, hydrate at the end. So let's look at cobalt chloride, right? Cobalt chloride, actually I think it's cobalt 2 chloride. Cobalt 2 chloride, and then there's 6 waters. 6 is hexa, so we would say cobalt 2 chloride hexahydrate. What a name. You know, Epsom salt, if you've ever had sore muscles, they usually tell you to take an Epsom salt bath. Epsom salt is magnesium sulfate, so MgSO4, or actually Mg2SO4, so it's magnesium sulfate heptahydrate. So there's 7 water molecules around it. So I want you guys to just think about this a little bit. I want you guys to practice naming some ionic compounds, and then I'll give you guys even more. It's just MgS. Anyway, I want you guys to name more compounds on your own to see if you guys can start working through a few of these different problems, and then let me know how it goes. We'll definitely have enough practice before the first exam. This ends part 1, and hopefully it was you know, have all the questions answered. See me if you still have questions, and then part 2 we're going to continue to name things and seeing how to name things, and then we're going to start talking about what we can do with these molecular formulas.